Okay, so hello everyone and welcome to another ICTS virtual string seminar, which we are resuming after a 2-week break. So today we are happy to have Soumangsu from TIFR with us. So over to Soumangsu, if you're ready.
Thanks, Vishal. Thanks for the invitation. I've never been to ICTS in person. I would love to be there physically, but maybe when the world comes back to normal. So I'm mostly going to talk about this paper that came out end of last year, and mostly going to focus on the content of these guys, but also they'll quote results from other papers. And I mean, some of those are old results where they talked about cosets and cosets as good string backgrounds and all. So as the title of my talk suggests, I'm going to talk about three relatively independent entities, which are like this. The coset or superstring in this background, in this coset background, it's a critical string background. And then you have NS5 branes wrapping T4 times S1 with some P fundamental strings wrapping the S1 and n units of momentum. And I'm going to talk about some marginal worldsheet deformation rather of string theory in ADS3 times some compact manifold. And the deformation that I'm going to talk about are these J minus, J bar minus deformation. And this particular deformation that is also known as single trace TTbar. I'm not going to go in details about what is single trace TTbar, why is it called single trace TTbar, but just for today's talk, I'm going to assume that this is what it means by single trace TTbar. So there are three independent quantities, and what I'm going to relate in this talk is that these three are equivalent descriptions of the same physics. So let me be a bit more precise. So as I told you, I'm going to study superstrings in this background. This is a three-dimensional background, SL2R U1 by U1. And then there is this S3 and times T4 or K3, whatever you wish to take. And this, I'm going to claim that this is the full description of the near horizon theory of KNS5 branes wrapping S3 times S1 with P fundamental string. So if you have, let's say, if you have this is the T4 direction, and this is the S1 direction, let's say, and then the NS5 branes are sitting here. The fundamental strings are like this, and there are n oscillatory modes along this F1 directions, and these are NS5s. And what I'm going to claim is that the near horizon geometry of just the NS5 branes in this whole setup is exactly given by this worldsheet string theory at weak coupling. And it has been shown that these two are related by this JJ bar deformation, or in other words, single trace deformation. And I'll also make comments how you can understand that this guy is equal to this guy, but I'm not going to go in details because this was kind of worked out in great details in this paper and this paper. And what I'm going to show is that the supergravity background of this superstring worldsheet theory is identical with what you obtain here and what you obtain here. Secondly, I'm going to calculate the string spectrum, mostly the long string spectrum from here, and we'll show that it agrees with the one that has been calculated in this picture from a few years ago, maybe more than that. And secondly, it also agrees with the spectrum computed in this picture by this Kutasov, Givion, Kutasov, Itzhaki in this paper some 3 or 4 years ago. And thirdly, I'm going to, if time permits, I'm going to calculate the 2-point function of two local operators here, on the space-time theory, and show that I'm going to argue that that 2-point function, one can also derive the same 2-point function using standard holographic trips in this background. Now, one thing that I want to stress at this point is that the asymptotic backgrounds that you get here or here, they are no longer ADS. Here you get okay, let me just stick to this slide. Yeah, so the asymptotic backgrounds that you get in this holographic examples are linear, a flat space-time with a linear dilaton, often called a linear dilaton background. And so already at this level, you can just this coset teaches us in some way how to flow away from ADS and study holography in non-ADS spacetimes, namely flat spacetime with a linear dilaton that is continuously connected to ADS. So whatever you calculate over there, you have the ADS limit where you can check whether it agrees with the results known from 20 years ago. So why do we study this coset? Yeah, I mean this, or rather, what I'm going to talk about in this talk is that these equivalent descriptions of same physics are always interesting. It's always good to have many different descriptions because some calculation is easier in one picture, some is not, and it's always good to have many different descriptions. Secondly, as I told you, that it may give us some systematic way of studying holography in non-ADS spacetimes. Thirdly, it's somewhere intermediate between ADS holography and absolutely flat space holography because the asymptote is no longer ADS, as I told you. So it's one step towards understanding flat space holography, although we are not quite there yet, at least from the approach that I'm going to discuss today. And finally, this will give us some insight into little string theory. So you can think of the space-time theory as a little string theory in the IR that flows to the CFT that we know in ADS3, like the dual CFT in ADS, the dual CFT, I mean the CFT dual to string theory in ADS3. And this, as I told you, this flow is something like this single trace TTbar that takes you from a CFT to little string theory. Little string theory, you have CFT too. So it gives rise to some interesting physics of a little string theory that is smoothly connected to a well-defined CFT2. So before I start talking about the coset, let me quickly give you a lightning review of certain aspects of string theory in ADS3. So string theory in ADS3, when just the NS B field turn on with no Raman RR sector, Raman sector turn on, Raman sectors are switched off. Only what we have is just the NS sector. And string theory, the worldsheet string theory in such a background is given by the SL2R Witten model. And this is a well-studied thing. And people have been studying SL2R Witten models for, I don't know, for maybe for more than 30 years from. So it's quite well understood. So the good thing about this SL2R Witten, or like any other Witten models, it has two copies of SL2R left and right current algebras. These are symmetries at level K, and the K is related to the radius of ADS3 as RADS is equals to square root times LS, and LS is square root of alpha prime. Now, the symmetry algebras are generated by these currents J plus J3, J plus minus J3, and J plus minus bar, J3 bar. You can think like in the angular momentum picture, is J3 is like the Z component of the angular momentum, and J plus minus are the shifts in the light cone directions. So basically, J3 is the generator of E plus L, and J3 bar is the generator of E minus L. And these are shifts in the transverse light cone directions. And as we will see that the symmetry algebra will play a very important role in understanding the spectrum of the theory, even in the case of in the coset model that I'm going to talk about, the spectrum, the correlation functions, as well as understanding various other aspects like Brst quantization and others that I'm going to talk about very soon. So now, with the ADS CFT correspondence, what we can say is that string theory in this background, ADS3 is dual to some CFT2 living on the boundary of ADS3. Now, when you have just the pure NS sector, as I told you before in my previous slide, the string theory, the space-time theory, when K is greater than 1, yes. So for my purpose, K is always greater than equal to 2. So when K is greater than 1, that space-time, I mean, the space-time theory has an SL2C invariant vacuum. It can be an NS vacuum that corresponds to global ADS3 in the bulk. We know what is a global ADS3. And it may also have an R vacuum, which corresponds to massless BTZ in the bulk. And this is what I mean by massless BTZ. So the NS sector states contains a sequence of discrete series states, whereas the continuum, it starts from, and also the continuum of long strings, the so-called long strings, which belong to the continuous representation of SL2R, and the short strings, they belong to the discrete representation of SL2R. And the continuum, the gap, there is a gap between the ground state and the continuum, and the gap is K over 2. people have been talking, I mean, people conjectured this gap or maybe came up with some indirect argument why this gap is k/2, but most concretely, or I mean, in the most algebraic concrete way of understanding of this gap k/2 was discussed by Maldacena Uguri in their first paper of ADS string theory in ADS3 papers. This series of 3 papers, the first one that talked about this k. Whereas in the R sector, there is also a continuum, but the gap is much less. The gap is 1/k. So for large enough k, the gap is very, very small. So in my talk, what I'm going to do is that I'm going to stick to the R sector and only the long strings. I'm not going to talk about the NS vacua, and I'm not going to talk about the discrete representation. The reason being the discrete representations are not very clear to me, at least in the R sector. So I told you that that string theory in ADS3 contains the short strings as well as these long strings. The long strings, the theory on living on a single long string was analyzed by Zyberg-Witten in 1999. I should have given you the archive number, but I forgot. So for string theory in ADS3 times n, the theory living on a single long string is described by a sigma model, M6K long, which I call M6K is the central charge, 6K is the central charge, and long is L stands for the long strings because I'm talking of only the long strings. And it's given by R5 times n. So this n is the same n here, the CFT, the CFT on n, and R5 is the dilaton direction, which you can think of as the radius of ADS3. I mean the radial direction of ADS3 sort of. Exponential of phi is the radial direction. This is this linear dilaton theory. So the R5 has a linear dilaton, as I told you. There is a linear dilaton, and whenever there is a linear dilaton, there is a slope. And this slope changes sign when you go from k greater than 1 to k less than 1, and that plays a big, and that's huge. That plays a huge role in understanding what the space-time theory is. But for today's discussion, I'm going to stick to k greater than equal to 2. Now, the string theory in ADS3, I mean, for example, if you consider string theory in ADS3 times S3 times T4, which is like this, perhaps the most well-studied string theory in ADS3 examples, it has the theory on a single long string has 4,4 superconformal symmetry, and M6K long is given by this guy. Now, one thing you can show that this effective coupling of the string, the effective coupling of the long string, it grows as you move towards the boundary, because G string, this effective coupling of the long string goes as exponential phi. And I told you that Q left in my example is greater than 0. So basically, it becomes the long strings become strongly coupled as you move towards the boundary. But there is a wide region in the radial direction where the strings are weakly coupled, and one can use string perturbation theory to understand the dynamics of those long strings in that particular regime. And that's where I'm going to stick to. I'm going to stick to that particular regime in the radial direction where I have perturbative string worldsheet control on the perturbative worldsheet theory. Now, a natural question that one may raise at this point is that what is the full boundary theory? And that's dual to ADS3 vacua. The answer to that question is not known. It's not known in general. We know for sure what's going to happen for k equal to 1, but in general, it's not known. But what is known is that if you just look at the theory of the long strings, that's described by the symmetric product, M6K long raised to the power P mod SP. So what is P? P is basically the number of F1 strings, which you can think as that the G string squared goes as 1 over P. That if you don't want to talk in terms of the fundamental string, the string coupling goes as 1 over P. So for large enough, this is the worldsheet string coupling rather. So for large enough number of fundamental strings, or if you want to work at weak coupling, weak string coupling, this P is quite large. It's a big number. And there are many evidences for this statement, why just the long string sector forms a symmetric product. But I'm not going to talk about that. It's not going to appear in my discussion, but I'm going to borrow some results that has already been talked about some 15 years ago in the literature. Now, let's go to the coset. The coset that is the hero of this story. So what I do is that I take SL2R at level K, U1. This is a compact. This is a compact U1. This x is what parameterizes the u1. So this is this x direction of radius, let's say r. And this w is what parameterizes the u1 that I want to get. And this is non-compact. So when I say that I have a coset or I have a u1 gauging, I need to tell you exactly how this u1 acts on this SL2R times u1. So basically you have SL2R times u1 divided by u1, and this u1 can act here, a little bit here, a little bit here, and I need to tell you exactly how this u1 acts. But let me just take 30 seconds out of my talk to motivate why I chose this particular coset. So one reason is that, very naively, without going into details, if this u1 acts completely on this u1, if this acts completely on this u1, what you get is the residual thing is just SL2R. But since it's non-compact, there will be some residual things that will make it a BTZ. Whereas when this u1 acts completely on this SL2R, then you get SL2R times u1 times u1. So basically, just by changing the gauge angles, I mean how it acts here and how it acts here, you can interpolate between SL2R and some SL2R over u1 coset models that has been studied, I don't know, maybe for 30 years ago by many people, by this Diagraph, Verlinde, and many others. Witten wrote a paper on the string theory in black holes in string theory, black holes in string theory, and some other papers as well. So this is a motivation that one may consider why you need to study, why it could give you some well-defined string background that will allow you to interpolate between ADS3 and this background is this flat space time with linear dilaton background, this SL2R over U1, and this has been well studied. So there is this, if you do the Euclidean gauging, that will give you coset. If you do the Lorentzian gauging, it will give you a Lorentzian black hole, and we will be doing the Lorentzian gauging. So let's look at the gauging that we want to do. So you take G as an element of the SL2R. G belongs to SL2R, and you have X left and X right, which parameterizes the U1. This U1 in the numerator, and you say that you declare that you do this identification, this particular identification. Now, if you look carefully, it's not a U1 gauging, it's more than that, because I have rho 1 here, tau 1 here, and rho 2 and tau 2. It's basically gauging U1 times U1. So it's basically doing more than that. So I have to tell you how these taus and rhos are related. So what I do is that I declare that the tau 1 and tau 2 are related in this way, in this equation, by this way, and chi's are some given numbers. You are given chi's once for all, and so basically that fixes the dependence between tau 1 and tau 2. Now you want to have a theory that is anomaly free, and once you impose anomaly free condition, it's going to give you is that the rho vector is related to the tau vector, and this is some rotation. I mean, basically what it's going to give you is that rho squared is equals to tau squared. And from there, without loss of ambiguity, you can think of that rho and taus are related by this nice rotation matrix. So now we have 4 variables, 2 constraints. So basically we are left with 2 variables that's going to parameterize my U1 gauging, which is like this U1. We have 2 because there is this left and right movers. The corresponding parameter for the U1 left and U1 right. Now, using the standard procedure for gauging, what I'm going to do is that I'm just going to write the gauged Huiz-Zumino-Witten.
Hello.
Yeah.
Can I ask a question about the previous slide?
Yeah, absolutely.
So I'm trying to understand this claim. So this particular gauging, is that the statement that it kind of interpolates between these 2 limits that you mentioned?
Yes. So basically it's going to interpolate between, so if this, where is my pen? Yeah. If this acts completely on this one, you will get ADS3. It's like this E1 cancels, or at least some space-time which is asymptotically ADS. And when it acts completely on this one, you will get a space-time which is asymptotically linear dilaton space-time.
Yeah. So how do I go to these limits in this in these terms of 1,000 rows and so on?
Yeah. So for that, I need to tell you what are the gauge currents, right? I mean, once I tell you how this U1 acts, there are some I need to tell you what are these guys. Once I tell you that, you can just completely determine exactly in which U1 subgroup of SL2R times U1 you want to gauge. I'm going to show you in the very next page what is my gauge currents, and then it will be clear.
Okay.
So using the standard procedure, I mean, people have worked on these gauged with Zumino-Witten models quite a lot in the olden days of 90s and all. So basically, the way you write the gauged with Zumino-Witten action is exactly this form. So this is the with Zumino-Witten action of SL2R. SL2R. This is the U1 gauged with Zumino-Witten action, and when you gauge, you get these extra terms. This A is the gauge field, J is the gauge current, and then there are also other terms. And this is the gauge currents. Now let's see. If I set this quantity to be 0, then it only acts on the Jx. Jx is the current that so you have SL2R times U1 in the numerator. Jx is the current that generates this U1. So if you set this quantity and this quantity is to 0, there is some value of psi and chi and psi in such that these two quantities just drops out, and then you have this U1 in the denominator acts entirely on this U1 in the numerator. Similarly, if you drop this particular term and keep this term, then if you drop this term, sorry. If you drop these two terms, then it acts completely. This guy acts completely on this U1, and this U1 is just a spectator; it's doing nothing, and that's when it will give you the linear dilaton background. So this is this part when this J acts on this SL2R. This is this D diagram Verlinde paper from 91, 92. And one more thing that I want to specify is that this action that I have, that I write here, this is a gauged action, but not gauge fixed yet. So this still is invariant under gauge transformation. So if you just try to see this whether it's invariant, it will be invariant. We haven't fixed the gauge yet, so there are still redundancies we need to fix. Now, yeah. So these gauge currents, they are normalized in this particular way. And it's not going to be necessary here, but ultimately at some point it may be interesting. It will be interesting to calculate the Brst currents and all. That's normalization will be necessary. So given an action of this form, and if you don't say anything, the first thing we physicists do is that integrate out the A fields, because there is no kinetic term for the L field. If you're asking anything about what's going on, we just integrate out the gauge fields. And the same thing we do here as well. Once you integrate out, you get this gauged action. And there is also a dilaton that can be calculated from the transformation of the measure, because yeah, there are standard ways of calculating the measure, and that's how you calculate the gauged action once you integrate out the gauge fields. Now, you just need to be careful that you.
Sorry, can I just so sorry, can I just go back to the previous slide? So here the claim is that for every chi and psi is a distinct theory. There are no other.
Yes.
Like there is no other duality or anything which relates.
Right. So basically, what's going to do is that if you look at the supergravity background, so let's say you fix chi and psi, you get a supergravity background that has a black hole, and all you need to know what are the positions of the black hole radii. I mean the horizon radii, the R plus and R minus. So this rho and so you give me two values, I will give you two values of the inner and outer horizon radius, and that fixes the background geometry. You change those chi's and psi's, that will give you a different geometry.
Okay. So all these are distinct geometries. So there's an S1 cross S1 worth of.
Yes, right.
Geometry.
Yes.
Okay. That's a moduli space of. That's actual moduli space of like these choices, or.
I mean, it's not a moduli space in the sense that I mean, well, okay, you can call it a moduli space, but you can think like to know, I mean, how do you exactly, so given a black hole, how do you know it's, how do you know everything about the black hole? You have to be told the inner and the outer horizon. So, so that's how you know, that's how you can say that that it's the moduli, but it's not exactly a moduli in the usual sense, right? In the usual sense, we talk about moduli.
Yeah, that's okay. That's okay. Yes, that is fine. But I'm just, so but the inner and the outer horizons are determined by two angles. This is somewhat confusing.
It's determined by two angles. Yes, it's determined by two angles. So basically what will go is LS, the string coupling LS, and the number of the level of the SL2R, and chi and psi. These are the data that will go in. And also the asymptotic value of the string coupling.
And I mean, why is this space, you know, why is there a compact parameter, or is it just something?
I mean, it's not compact. It's not compact in the sense that you can make the horizon size anything as you wish, because it's not going to be a compact.
But eventually it is specified by two angles.
It's eventually specified by two angles. It means that it will start from, let's say, 0, it will go to infinity, and then it will again start from 0 and go to infinity. But it's not that the rho plus and rho minus will be bounded.
Okay. Okay. Okay.
Okay. So, and one more thing that we need to be a bit careful about is that the denominator, which is which shouldn't be 0, and that's you just need to take care of that. Then the gauging breaks down. So this guy is still gauge invariant, and what we will do is that we will gauge fix it, and once we gauge fix it, we get the three-dimensional geometrical interpretation from the sigma model, from this whole gauge sigma model. Then we can write you the metric, the B field, and the dilaton. So for that, we just choose some parameterization that's convenient for us. So theta is kind of the radial direction. Theta can go from 0 to infinity, and these alphas are the two other parameters, alphas and betas. And I choose this particular gauge fixing, and this gauge fixing will break down if we choose chi's and psi's in this particular. I mean, for these particular values, the gauge fixing will break down. The reason being that this denominator will become 0 for these particular values of chi's and psi's. So other than that, everything is fine. And now we just have the parameterization. We plug it into the gauge action, and this is what we get. Well, there is this guy becomes a bit complicated looking. These are the j's. Y is kind of the time direction. Jx is this direction along the spatial circle, and theta is the radial direction. So, and then just using standard worldsheet techniques, let's read off the metric, the B field, and the dilaton. Now, this metric, if we look at it carefully, it doesn't resemble anything that we have seen before. It's not a nice looking metric. But once you do these coordinate transformations, what you get is that a metric, a nice looking metric that kind of we have seen before. So let's forget about this L for the moment. Let's say there is no L. I'll come back to this L. This L, there is no L. And what you get is exactly a BTZ. Now let's bring back the L. So in L, if you look at the expression for L, the expression for L is this guy. Now let's say rho is much, much less than this guy. So basically, all you do is that instead of writing rho equals to this whole thing, I will just put this twice chi LS squared in this sine chi and sine chi minus psi here. And then I can absorb it inside this dt and inside this dx and dt, and that's still giving me BTZ. So basically what happens is that, if this is the rho direction, so there is some transition region determined by when this quantity and when this quantity and these quantities are comparable, there is a transition scale. And here you have BTZ. And when this quantity is much, much bigger than this guy, then you just replace it L squared by rho squared. And that you can compare it to be the linear dilaton black hole. I mean, you can just quickly see if you set rho plus and rho minus, this will be rho plus. Similarly here, if you set rho plus equal to rho minus, then you will, rho plus equal to rho minus equal to 0. This is going to be exactly a linear dilaton times S1 background. And then when you have rho plus and rho minus not equal 0, you have a black hole in it. And this is the question that Loga was asking, that I can express everything in terms of rho plus and rho minus. Sorry, rho plus and rho minus in terms of the skies and size. And as I told you, this background interpolates between BTZ in the IR. So if you go very deep inside, so you fix the horizon somewhere deep inside, you go very close to the, or let's say that we go to the 0 temperature case, or maybe this slide is very good. Yes. So this is the same sigma model when I take the rho plus equals to rho minus equal to 0. Rho and phi are related this way. This is the usual ADS3 coordinates that we use often. And this interpolates between linear dilaton in the UV to ADS3 in the IR. And when you turn on a temperature, it just interpolates between BTZ in the IR to some two horizon, two charge black hole in the UV in asymptotically linear dilaton background. So yeah, so this brings me to the end of the sigma model description of the worldsheet theory. Now let's look at the NS5+F1 system. So I claimed at the very beginning that the coset description is going to be the theory of the full theory of the near horizon limit of the NS5 branes in a system of NS5 plus F1 plus momentum. So what I do, I take this NS5 branes on a torus, and there is this times S1, this T4 times S1, this is S1 direction. I put the fundamental strings here with n momentum going along this S1. And this is the metric that people have written down, I don't know, 30 years ago. So here you have an S3 that doesn't decouple from the radial direction. I mean, the S3, the size of S3 grows, as well as there is a T4. The T4 is already decoupled. These are the harmonic functions. Rho R0 can be thought of as a non-extremality parameter. If you take R0 equal to 0, it gives you a PPS solution. And then you have the other harmonic equations. I'm just copying from some old paper. So this is nothing new here. Now what I do is that I want to go to the decoupling limit of the NS5 branes. So as in any holographic examples, what I do is that I take GS and G goes to 0 such that, and also I go to distance scales of order G times LS such that this quantity is kept fixed. In that limit, we get F5 is equals to KLS squared by R squared. K, I remind you, is the number of NS5 branes. And this R5, yeah, this R5 is basically this will become the radius of ADS, but it's given by R5 squared is equals to K in string units. And this is equivalent to taking the near horizon limit of the NS5 branes. So, I mean, technically what I'm doing is that I'm taking this F5 equals to 1 plus R5 squared by R squared, and I drop this one. What I have is that F5 is equals to this quantity. And that's what we mean by going to the near horizon geometry of the NS5 branes. There the background is given here. It's just one line algebra. But something funny happens is, I mean, something nice happens is that this ADS S3 times T4 decouples. This just becomes spectator. Their radius is no longer growing with respect to the radial direction. And there is also the B field and the metric. Then let's consider this change of coordinates, a simple change of coordinate. And once you do this change of coordinate, this metric takes exactly the form that I derived from the coset. This rho plus and rho minus are given by this expression. So there is also this L squared. And when I say they exactly match the example that, I mean, the coset, the supergravity background I obtained from coset, what I mean is that they match once I do this identification. So on the left-hand side, I have the microscopic descriptions like the fundamental strings and number of fundamental strings. Alpha 1 depends on the number of fundamental strings. This is dependent on the n. This is the non-extremality parameter. And on the right-hand side, you have these phi's and chi's and k's and k's. And this, yeah.
So do you drop the 1 from all 3 harmonic functions?
No, I just dropped the 1 from the NS5 branes. I am in the near horizon geometry of the NS5 branes, but I am far away from the fundamental strings. So you just drop this one. Where is it? Yeah, this one from F5. And that's the decoupled theory of the NS5 branes. That's what you do. So forget about that you have NS5 F1 strings. If you have just NS5 branes, if you want to look at the decoupled theory on the NS5 branes, that's what you do. And the funny thing is about NS5 branes is that I forgot to mention this comment, that the dynamics of the NS5 branes decouples from the bulk even without taking alpha prime to 0. Usually that doesn't happen in D3 branes, for example, ADS5 plus S5. If you want to decouple the dynamics of the D3 branes, you have to take the string length to 0. But here, to get a decoupling limit, you don't have to take alpha prime to 0. And that's what shows that the decoupled theory on the living on the plane, they are string-like. But there is no gravity because you already have set G string to G to 0. There is no gravity, but it's still string-like. I mean, it's a non-local theory, but there is some finite alpha prime. In fact, it can be shown that the string scale of LST is square root k times square root k times ls. Yeah, the alpha square root k times alpha prime. So this is the effective length of the little strings, not the strings. The strings that doesn't know about gravity, but knows about the string finite size of the string length. And that particular theory is there is a name for that. It's called little string theory. It's a decoupled theory on the little just on the NS5 branes. So basically what I concluded is that the full near horizon theory of the NS5 branes, just the near horizon geometry of the NS5 branes, plus the F1 strings and the momentum along that S1. This whole theory is described by this SL2R times U1 by U1. Given that I do the gauging with the gauge currents that I've shown before. So this is exactly what I meant. I mean, maybe I'm repeating myself here. So basically, if you look at this NS5 plus F1 plus momentum system, there is asymptotically, there is flat. This is R10. And then in the near horizon geometry of the NS5s, you get a linear dilaton spacetime. And then when you go even closer to the fundamental strings, that is, if you drop the F1, you drop the 1 from F1, you get ADS3. You drop that, you set this 1 to 0, you get ADS3. So this is when you go to the near horizon geometry of the fundamental string as well as the NS5 branes. Here you are only in the near horizon geometry of the NS5 branes, and here you are just far away from everything. So here you see a 10-dimensional flat. So my claim is that this whole theory, this whole worldsheet theory, is described by this guy. So
sorry, I have a question.
Sure.
In that linear dilaton regime, when you're dropping the 1 only from the NS5 brane factor harmonic function, is it actually a solution of the supergravity equation?
Yes.
That can be checked, is it?
So yeah. You just take this equation. Forget about the F1. Just keep only. So take this equation. This equation. Forget about a finite temperature. Set R0 to 0. Set R1 to 0. Set Rn to 0. Keep only R5 and set F5 is equals to.
In that case, I do know that. But when all the 3 harmonic functions are present and you drop 1 only from F5, that is a solution.
Yeah, that's a solution. And I mean, with the 1, it's a solution. Now you just think that you just go to very close to the near horizon geometry. There, this term dominates. This term dominates. Think like R5 is much smaller than R square is much smaller than R5 square. Then this term just drops out. And then all you are left with F5. So you have shown the more complicated solution to be a solution to of your supergravity equations of motion. Now what you are showing is that in a particular limit of R, it's still a solution. It's not even, I mean, once you have shown, you've done the difficult job of showing this to be a solution. Now A particular limit of that is what I'm talking about. That's the dropping this one. Does it answer your question?
Okay, maybe, but I'm not very sure that the limit commutes with differentiation on R and all that, right?
So then you can just try this. You take this solution. Just take this solution and plug it into the worldsheet beta functions or the supergravity equations. Just take this one because
I think that is certainly a better argument. Yeah.
Okay, so just plug it into the supergravity equations and check that they will satisfy.
Yeah. Okay. Thanks.
Excuse me. Can I also ask a question?
Yeah, sure.
So when you drop one from F5, but not from the one which is for the string, let's say, does it impose some relation between? Can you go one slide before? Yes. Does it impose any relation between, say, R1 and R5? Saying
No,
like,
it doesn't give any relation between R5, but there are some constraints. For example, you know that these are the constraints, right? There are 3 parameters. So you have alpha. Let me clear this page because I have too much junk.
What would it mean physically? I mean, when I drop one from the NS5, that means that I'm very, very close to the NS5.
Exactly.
When I don't drop that from the F1 string, it means that I'm still too far away from the string, and that means that the R5 is much smaller than R1 or something like that.
So R5 so basically what you do is that you have, let me draw the so let's say this is your space time. You have this throat of the NS5 branes. So let's choose some scale which is let's choose some scale which is here, which is like R hat is equals to R0 by GS by G.
Mm-hmm.
So you choose this scale, you set G to 0, you fix this R hat. That what it means is that you are effectively sending this is the flat 10-dimensional geometry, which is far, far away from everything that you have. So when you take this limit G goes to 0 and keeping this fixed, this quantity fixed, and concentrating on in the distance where R is of the order of G times LS, what it means is that you are effectively sending this flat part much, much far away from this scale R hat. So basically all you are going to see is the throat region.
Okay, and this then should now affect the F5, but doesn't affect F1. And then that means that there's something different in R1 and R5.
Yes, yeah.
And what is the relation between R1 and R5?
I mean, R1 and R5 you can figure out. So for example, you have this as R5 and you have these relations. So R1 and R5, and they are given by these expressions. So you can relate and you can find out a constraint. It's not a linear one, but you can find out a constraint.
Okay, I see. Thanks.
So yeah, so far we are done with the NS5 branes and the coset. And what I'm going to argue is that I'm not going to go in details because this is not the main topic of this talk. But I'm going to say that the same background you obtain when you do this J minus J bar minus deformation of ADS3 in the pure NSNS sector. So for simplicity, let us look at T equal to 0 case, the 0 temperature case. This is the string theory in ADS3 Lagrangian with NSNS sector. Phi is the radial direction, or you can think of exponential phi is R or rho, whatever. And you do this deformation. So when I write this deformation, it's not exactly telling it the right thing. It's basically what I'm doing is that delta L delta lambda is equals to J minus J bar minus. So I'm solving this differential equation. And once you do that, you get this deformed Lagrangian. This is an exact deformed Lagrangian, and this is known in the literature as single trace deformation of TTbar deformed CFT, ADS3 CFT2. And if you compare with this guy, where is it? It's exactly the same thing. This is exactly the same thing, except there was a lambda here, but lambda is some fake parameter. I mean, you can just change phi, you can absorb inside phi. Phi goes to phi plus log lambda, something like that, and then rescale these gammas such that this lambda just disappear. So this is the same thing. And similarly, starting from the worldsheet model of a BTZ, performing this J minus J bar minus deformation, you can land up in the full geometry at finite temperature. That's just a messy thing, but it has been done. but the calculations are a bit complicated. So yeah, so this brings me to the equivalence at the level of the supergravity or the sigma model. Now what I'm going to do is try to find the spectrum using Vrst quantization. So if you have a gauged Huiz-Zumino-Witten model G over H, and for the moment, let's assume that H equals to U1. For non-abelian, there are some subtleties which I don't want to talk about. And you gauge fix this way, that a bar equal to 0, that the anti-holomorphic component of the gauge field is 0. That's how you gauge fix it. Then the fun fact is that the total gauge fixed Lagrangian takes this form. This is the Huiz-Zumino-Witten model of the group G. This is the Huiz-Zumino-Witten model of the group U1 or H, and there will be some ghost coming from the determinants of this BC ghost, you know, when we do Vrst quantization for the Popov ghosts. And in our case, what is going to give me is that this is the SL2R plus U1. This is the U1 coming from the denominator, and then there are some ghosts. Now, notice one thing is that this action comes with the wrong sign because it's a negative, not a positive one. And this going to save us, or we know that there will be ghosts and there will be negative non-states, and this is how it appears, that there is this negative non-states, and we have to kill those negative non-states. That means we have whatever state we calculate, whatever Hilbert space we declare, we have to show that this Hilbert space is Vrst invariant. Now, we do the usual Vrst transformations. These are the usual Vrst transformations. And this Ka eta is an arbitrary Grassmann parameter. J, I remind you of it's the gauge current. And what else is there? And I think the rest have already defined. So once you do that, the change in the S total, which is the total action, is given by this action. So from there you read off this as the J Vrst, and an easy way to check that Vrst charge squared is Q squared Q Brst squared equal to 0 is that Jj has regular, I mean the OP of Jj is regular. And for that you just use the standard current correlation function of AD of SL2 or Huiz-Zumino-Witten model and U1, and it's trivial to check. So all physical states that I want to calculate must be invariant under Q Brst. So let's try to see what kind of states are allowed. So we will do in the language of vortex operators. And again, this is some thing that I'm quoting from literature that I mean people have talked about 30 years ago. That if you have a G over H gauged with Zumino-Witten model, the vortex operators can be written as G times G of the denominator. Sorry, vortex operator of the numerator into vortex operator of the denominator. And then you have to impose that this V is annihilated by the Q Brst. So it's very simple. You take the vortex operators of SL2R times U1, which we know. We take the vortex operators of the U1 of the denominator, you multiply them and impose Vrst invariance. So that's what I do here. So I have here the vortex operators coming from SL2R. These are the low-lying vortex operators in the continuous representation of SL2R in this so-called M basis. This is the vortex operator or the tachyon-like vortex operator in the U1 in the numerator, and this is the vortex operator coming from denominator. Since the denominator U1 is non-compact, I have only one momentum kappa, not kappa left and kappa right. And P left and P right, we know that they are given by this N over R times plus minus omega R over L squared, and this M's are the J3 eigenvalues because of this Lorentzian ADS3, Euclidean ADS3. There is an annoying factor of I here that doesn't appear in Lorentzian, but it appears in Euclidean. So once you do that,
is the radius of the compact direction fixed because of supersymmetry or anything, or no?
Compact, I think I fixed it from the beginning. I just declared my U1 to be something, U1 in the numerator, you mean, right?
Yes.
Yeah, I just declared it to be of some radius R. It's a moduli, you can think of that.
I see. Okay.
Yeah. Like this X is identified as X plus R or 2 pi or something. I don't remember which one I took. So yeah, so this is the BRST current. And once you impose BRST invariance, that means you demand the OP with respect to the BRST, OP of the BRST operator, sorry, the OP of the BRST current with respect to the vertex operator is 0. That will give you two constraints. So whenever you define a vertex operator, there are these M's, there are these kappas, and there are also these P left and P right. And on top of that, you impose that will give you the physical Hilbert space. And this kappa you can just eliminate to write it in terms of one single equation. It's not very important. So now we have kind of the full Hilbert space. We write all the vertex operators in the way I described in my previous slide and impose these BRST constraints. So now we want to calculate the spectrum. So to calculate the spectrum, what we do is that we write the.
Sorry, just 1 minute. So, I mean, I'm trying to understand this. So this is basically a conformal. This is a conformal worldsheet theory.
Yes, it's a conformal. It's a conformal worldsheet theory. Yes.
So, I mean, what happened to all the other stuff?
What do you mean?
Made it into the super conformal field theory.
You mean the so basically you are saying that I'm talking about ln's and ln bars, and what about the g's?
Yeah.
Yeah, I think that will just first of all let me see, because I'm talking about a worldsheet model that's non-BPS because I have a finite temperature. So maybe if you work in the, so maybe these are important when you do write the super partners. But that I think it's
no. Let's just speak. No, sorry. Just 1 minute. So the worldsheet theory is always supersymmetric.
Yeah, the worldsheet theory is always supersymmetric, but
even if you're considering some black hole background or something.
Yeah, right. And
I mean, the space-time supersymmetry is a different thing from worldsheet supersymmetry.
Absolutely. So this G, what is going to impose is like the C equal to 15. And I think the rest, what it's going to impose is like whether you have a Raman boundary condition or a Nevu-Schwarz boundary condition, what are the number of ground states, the usual thing we come across in flat space. But maybe one needs to take care of a little bit more. It's I think it's
no, but the whole spectrum would have various things, right? I'm kind of a bit somewhat puzzled by, you know, like you would have beta gamma system. You would have a lot of things, right? I mean,
but the beta gamma system is going to, yes, right. So if I write the full vertex operator, what I'm going to do is that the vertex operator is V bosonic into V fermionic, and this will know the beta gamma worldsheet ghosts, right? Along with some VBC. That's what you are talking about?
I'm not. So I'm trying to understand what you're trying to say. Are you saying this is some universal sector where you don't have to analyze the worldsheet fermions at all?
I think the worldsheet fermions are.
Is it what is being said? I mean, I'm trying to understand.
I think so, because when I do the gauging, it only knows about the bosonic sector. I didn't tell you anything about the fermionic sector, right? I think the fermionic sector stays as it is, but I may be wrong.
I mean, the supersymmetric ADS3 does factorize into the bosonic ADS3 and
so in the coset case, I think the fermionic sector will just factorize sit on one side, I think.
Okay.
Shuja, is it right?
Yeah.
So you're saying that this coset does not touch the fermions at all, and it still preserves.
Yeah, I think so. The worldsheet supersymmetry is not hampered at all.
I don't know this very well.
Okay, but yeah, that's a good question, though. I'm not sure about exactly. Yeah, because
yeah, I mean, I'm just slightly thinking about, like, I mean, how can you just figure out the spectrum and the BRST cohomology and everything without just ignoring all of that? It's a bit.
No. I mean, with the other part, I think it's the argument with the same argument that you have in the case of ADS3 fermionic sector, the pure fermionic sector of ADS3, I think, the worldsheet fermionic sector of ADS3.
Okay, okay. So this is something that is known, that has been checked, or it's a plausible argument? Or?
I don't know of anyone actually checking these things, but when people talk about different backgrounds, deforming ADS3 and going to different other backgrounds, they never talk about the supersymmetric part though. So
no, but okay. I mean, it might be that in some, I can understand in some backgrounds, maybe you can analyze the spectrum like this, but okay, yeah. The question is that in the particular background that you're talking about, is this a legit thing to do, and is it known, or is it like, are you saying that, you know, like it's plausible that it is? I mean, what is the what is the strength of this claim? That's like
sorry.
somebody has shown that it works, or
yeah, maybe Shuja knows about what happens exactly in ADS3. Shuja, do you want to comment?
No, I mean, in the Ramon sector, we also need to bosonize the fermions and write the spin fields and so on.
Right.
You are in the Ramon sector right now?
I'm in the Ramon sector, but since I'm not touching, I mean, all this this gauging or the cosets, whatever I'm doing is only at the bosonic sector. So it seems naively that the fermionic sector is just a decoupled thing that you did it for ADS and the same result will be true. But I think what Loga is asking that how do you know that? I mean, maybe there should be other constraints that, or is it? I mean, once you include the fermionic sector, is it still a good superstring background?
Yeah, it needs to be checked.
Yeah, I think that needs to be checked. Yes, I agree. Yeah.
Maybe what you're saying is that there is in some picture this spectrum thing is.
The picture is always this.
Maybe something like that.
Yeah,
I mean, okay.
Picture number -1. I mean, these operators you write is as d2z e to the power minus this worldsheet superconformal ghosts times v. These are this -1 picture. Because when you impose the on-shell condition, this means that whatever sits here are dimension half object.
Sorry, so but then you are in the NS sector then, is that correct?
I'm in the Ramon sector of the space-time theory.
The space-time theory, okay.
Yeah. You mean the worldsheet? You were talking about the worldsheet one?
Yes.
I mean, in the worldsheet it will be NS. Yes.
Okay, I mean, yeah.
But you can have from both NS and R sector of the worldsheet to a given sector in space-time, right?
Yeah, but I think you can just fix the, I mean, if you have, let's say, so if you start with the global ADS3, that would correspond to this NS sector of the space-time theory, right? And I mean, when you say NS again, it's the worldsheet NS or the space-time NS?
No, I'm just saying that if you are, whether you restrict yourself to a particular space-time sector,
yeah,
on the worldsheet, both sectors can.
Yeah, both sectors will be contributing. That's also right. That's true. Yeah. So then which sector is it? Because that would imply that I need to get information about the fermions, right?
Yes.
Yeah, maybe that's where the fermions may impose some constraint if they are at all.
So what are you going to do about things like GSO and so on? Or you're not?
I think GSO. So there is this well-defined notion of GSO projection in coset models as well. So that's what you do. It's like in ADS3 there is a well-defined notion of GSO, and in ADS3 is like SL2R.
I understand that you can do GSO, but I'm just saying that in your thing, if you're not considering anything, then how are you going to project out to the states and get the correct spectrum?
Yeah. Right.
You know, like, I mean, in this way of doing it, how will you impose the GSO? I mean,
I
agree that
GSO.
there is a GSO in ADS3 and so on. I mean, but,
I can't impose GSO. The reason being, yeah, as you said, that I'm not considering the superstring spectrum. Sorry, the fermionics part. Yes.
But then, you know, like, how would you know what the spectrum is? This is what is concerning me. That how would you know, like, for example, what the, I mean, there's a difference between, like, say type 2A and type 2B comes basically because of GSO, right? I mean, like, you won't be able to.
Yeah, this which chirality you choose.
Yeah, all these considerations are just swept away. I mean, with, you know,
typically in the ADS3 backgrounds, what Givion Pacman shows that there is a chiral GSO you can always impose. You define your space-time supercharge and you on the left and the right. And then you demand locality with respect to this operator.
Mutual locality with respect to this.
That's some kind of chiral GSO assumed.
Yeah,
but shouldn't you have fermions to do that, Sujay? I mean, like,
absolutely, yes. You should.
You should have the fermions, yeah, right. Yeah, maybe here we can do the same thing, right? You write the vertex operators, impose the BRST I mean, so yeah, write the vertex operators, and then you impose this mutual locality with respect to the chiral GSO that Sujay was talking about. But since it's a coset, since it's already gauged, I need to. I'm not sure exactly the same arguments will go through or not. This is something I'm not sure about.
Okay.
Yeah, it's a nice question that you raised.
Yeah, I mean, you understand why I'm kind of.
Yeah. I completely understand that, because then what am I? Why do you? What's the meaning of computing the spectrum if you don't keep the fermionic part and impose BRST, or sorry, this GSO, the fermionic part.
Okay.
Yeah.
Okay.
But usually what happens is that in fermionic strings, I mean, when you do superstrings, you impose you declare that your vertex operators in the -1 picture, and then you go on calculating the spectrum. But that's what usually people do. But what happens to the fermions, it's not very clear right now to me. Like in bosonic strings, they will just replace this half by 1. This half goes to 1. That will give you a bosonic answer. That's how it's approached. But it will be nice to see with the fermions as well. Okay, let me carry on with this, but I don't have a good answer to your question. Yeah. So we calculate so to calculate the spectrum, all we need to know are the dimensions of the vertex operators. And the way we do is that we take OPE of the vertex operators with respect to the stress tensor, and we set the on-shell condition. So the stress tensor, the first term is given by the Sugawara of the SL2R. This is the stress tensor of the U1, and this is the stress tensor of the U1 in the denominator, but notice the difference in sign, because one comes with a positive sign, the kinetic term comes with a positive sign, other comes with a negative sign. And there is something from the compact part. So once you do that, you get this as the dimension of the vertex operator. These are this J are this angular moment, this J3 spin, the SL2R spin. PLP right I defined before. K is the momentum along the U1 in the denominator, and delta N is the dimension, the contribution to the dimension coming from this compact part. And yes, so that's these quantities are delta left and delta right. You impose the on-shell condition. That means the total dimension of the vertex operators is half, where I use the -1 picture number of the yeah, we are in the -1 picture number sector. And then you just add these two. There is delta left and delta right. You add these two, you get this equation. You subtract, you get this equation. So I'm going to claim that this kappa is the energy of the system, or energy spectrum of the system. How I do that? I write so this is the claim that kappa is the energy spectrum of the system. So what I do is that I take the vertex operator, the full vertex operator, and I know that if I take the radial distance to infinity, it should better give me a plane wave in the transverse directions. And I also impose the BRST constraint. So once I do that, I see that after all the dust settles, because there is a formula for this VJM bar from 25 years ago. You just take this formula, you multiply with the S1 V e to the power IP, sorry, e to the power IPL X left and e to the power whatever you need to add. you take the radial direction to infinity, and you get a plane wave. And this coefficient should be the energy. And that's why I claim that this K is the kappa is the energy, and kappa is indeed the energy. Now, I could have stopped here. I don't need to do this, but I'm doing it because I want to derive the zamological spectrum of TTbar deformation. And what I do here is that I subtract the energy of a BPS string that has winding W along a radius of circle R. That is, I subtract. It's a constant shift of the energy. And once I do that, I get this. I could have stopped here as well, but let me just go on and derive the zamological spectrum. What I do is that for that, what I do is that I just go to massless BTZ, no deformation, nothing. It's in massless BTZ, what happens is that the long string sector takes this form. You can derive this expression from here as well. You take little ls to 0, and you will end up with exactly this equation, this one. Now, it has been pointed out long ago, almost 20 years ago, by more than that, by these people, that this is also the spectrum that you obtain when you consider a symmetric product, and you look at the ZW twisted sector of the symmetric product, and so basically you consider this. I told you that the long string sector follows a symmetric product. You take the long strings, you look at the ZW twisted sector. Such a state has such a long string is an operator in the space-time theory with dimension h of w, and this h of w is related to the dimension of the untwisted operator h1 in this particular way. And once you put here, you will see that this energy of the ZW twisted sector is exactly given by the same form that you obtain in massless BTC. So why am I telling you all this? It's just because what it means is that you can replace this part that you have here in terms of these H's, H1 and K. And once you do that, you get this expression, which is nothing but which is the energy of in the ZW twisted sector or Z omega twisted sector of the long string sector of the space-time theory. And I'm interested only in the W equal to 1 or omega equal to 1. And this is exactly the zamological spectrum that zamological obtained in TTbar deformed CFT2 for the unitary sign of lambda. Now, this is very important. It only agrees when you, of course, it's a CFT calculation. It agrees when you do this identification. So basically, this is one of the reasons why this J bar minus deformation is called single trace TTbar, because in the winding one sector, it indeed gives rise to the TTbar deformed long string theory, the theory on the long string. So yeah, so this brings me to the end of yeah, by the way, so this is also the spectrum. So this is also the spectrum that one can, not this one, this one. This is also the spectrum that one can calculate in this NS5 plus F1 plus N system going to the near horizon NS5 plus F1 plus N system. So this shows that at least modulo the comments that modulo the issue raised by Loga, and it's the three spectrums of the three different sectors agree. Now, let me quickly talk about the correlation functions. I don't know, I can show you an expression because I don't know the physical interpretation of the correlation functions of the deformed or of the coset or the deformed theory rather. But let me just show you how the correlation function looks like. Then you can comment on what physics it tries to tell us, other than it's a highly non-local theory in the space-time. So let's just quickly look at what is done in ADS3. So in ADS3, in the -1 picture, an operator in the space-time theory can be written as this. So this is nothing but what is usually called this Mellin transform of the operator J, V, J, M, M bar. I'm writing in the momentum space, P left and P right at the momentums of the space-time theory. And once you, I could have written X here, which is the position and positions of the space-time theory, but I want to express my final 2-point function in momentum space, so I'm writing in P. Then these phi's are vertex operators in ADS3. They are basically the eigenvalues of the Laplacian in ADS3. It's like the analog of e to the power ikx in flat space. And these are known. These are known from 98 papers of Zyberg, even before that, Teschner and others. there is also the compact, the vertex operator contribution coming from the compact part, and this is the compact part, 2-point function on the worldsheet. And once you just take this OP, O minus P correlation function, and that will imply calculating phi times VV, Vn. You do this Z integral, and all you get is this expression. This is all we know from our conform CFT2 literature. I mean, the 2-point function in a CFT2 takes this form, and in position space it's given in this way. So twice H is the twice H is the dimension of the operator phi, and operator of the dimension OP, more appropriate to say. It's a space-time operator. It's a operator of the space-time theory. It has dimension twice H, and we expect that this is to happen. Now let's do the same thing in the coset and impose Brst invariance. So what we do is that we have the phi, we have the operator from the U1 in the numerator, we have the operator from the U1 in the denominator, and we have the operator from the compact part. And we just plug it in here. Sorry, we don't plug it in here. We just use because these are operators of ADS3. So we know the phi 2-point function. These are operators, this exponential IP LX. These we know how to calculate e to the power IP left x, e to the power IP left x prime. We know how to do these 2-point functions. We also know how to do this function. We just do this exact same calculation, and we end up with this expression. So it's the same expression that I showed you here, except that this H is now a function of the momentum. Now, and this is, I mean, loosely speaking, it's not going to convey much message, but it's a signature of non-locality. So let's just look at a large momentum limit, high energy limit. So at high energies, what happens is that 2hp minus 1 goes as, so this is the only surviving thing, it's P. So basically what I'm saying is that this part, modulo this part, it goes as P to the power P to the power P squared to the power 2P or something like that, yeah. And this is a highly non-local behavior, whatever non-local means, that is not a local field theory like behavior, and that's what I mean by non-local. And I mean, it's, I don't know what much to say about it. And one confusing thing about this 2-point function is that it heavily depends on the normalization of the undeformed theory, of the operators of the undeformed theory. Let's say I take this expression. Let's say I take this expression, just this one. I normalize it here by some function of f of h, whatever you feel like, some good function of f of h. What will happen is that I repeat the same exercise. Here I will see this function of f of hp appearing, some momentum dependence appearing. And I don't know what to make sense out of it. So this part, it seems like it depends on the normalization of the undeformed theory of the operators phi. And this part is independent of the normalization. This is, I don't know, abuse of language in universal, whatever universal may mean. So this is something, it will be nice to understand that part, but so far I don't know what it means. And if you start with the supergravity part of this NS5+F1 momentum system, you take the near horizon limit, you just try to calculate 2-point functions using the standard way of we learned in ADS CFT in holography. You just try to do that, and you will arrive at exactly the same form. I didn't show you the calculation. It's a messy calculation, but it's not that complicated. We know exactly how to do in ADS. You repeat the same thing, you will arrive at this same thing from the supergravity approach. And so yeah, so this is another evidence that maybe these backgrounds are indeed the same, or they are, yeah, whatever. So this brings me to the end of
my. Just one question.
Yeah, sure.
So this 2-point function computation, I'm trying to decide whether it's really an independent check apart from the spectrum check, or is it like?
Yeah, I mean, it's not well, it's an evidence. I shouldn't call it a check, because I mean the spectrum is much stronger than the 2-point function, right?
Yeah. So I mean, if you, I'm just wondering if you get the spectrum right, wouldn't you?
Yeah, then you can argue
2-point functions, right?
They're bound to come out to be the same if you do your calculations right. That's what you are trying to say, I guess.
I mean, in the sense that Okay, another way to say what I'm saying is that an higher point function computation would be something which is like slightly more non-trivial.
Yeah, this ones I want to know. Yes. Yes.
Yeah, or OPs or what? Yeah.
Yes.
The
OP coefficients. Yes. Yes. Yeah, I absolutely agree with you. But so far I didn't manage to do that. Yeah. Right. Okay. So let's put it this way: the 2-point functions in this theory looks like this. And if you take this this LS to 0 or P to 0, which is the going to the near horizon region of the fundamental strings, where you expect to recover a CFT, and you indeed get a CFT. It's like this 2-point function interpolates between CFT2 to, let's say, little string theory in the UV. So yeah, so this brings me to the end of my talk. So what I try to argue is that this is this coset describes the full near horizon theory of the KNS5 branes in a system of NS5 plus F1 plus momentum. It is also the same as the single trace TTbar deformation of ADS3. And then we calculated the spectrum, derived homological spectrum of TTbar deformed CFT. That means the spectrum that you obtain from here as well. And yeah, so this 2-point function I calculated, but it's not, I shouldn't say it's a strong check, because if the spectrums match, that they do match. Yeah, but we have the 2-point function so far. Now, what can be done, but not sure exactly whether this makes sense or not, because these will be mostly speculations. And one thing that I want to do is to take the k equal to 1 limit, because if I define this PSU 1,1/2 times U1 by U1 by this particular way, that it only acts on this diagonal SU2, and then take the deep UV limit, that's going to give me the theory of one single NS5 branes. That's not known. So if we can do that, you do this coset in the supergroup formalism of Rajesh and collaborators using that hybrid formalism, then it could be a good candidate for the theory on one single NS5 branes. It could be. I don't know whether it's going to be or not. And in that case, we know an exact holographic dual for T4 T to the power 4 deformed by TTbar and its symmetric product. Basically, the symmetric product of T4 to the power T4 deformed by TTbar to the power n mod Sn. And this is exactly the bulk theory that I think it could be, but I may be wrong. And then, as Loga pointed out, higher point functions. What about higher point functions? Yes, these are things that one needs to calculate. And one, maybe it's ambitious, maybe it's just nonsense. What I'm going to say is that, so basically you have ADS3 times S3 times T4. So whatever I am doing so far is with this. Maybe we can bring this inside the coset such that it allows us to probe the asymptotic flash region of the NS5 brane. So if I draw this diagram that I had before, here you have R10, here you have linear dilaton, you have ADS3. I would like to go from here to here, but that's a long-term project. I don't know how to do. Maybe bringing this S3 here, because the radius of S3 blows when you go to the flash space region. It's not a decoupled system anymore. This thing just scales with the radius of the distance from the NS5 branes. Yeah. So yeah. So this is I don't know how it can be done. I'd love to hear if anybody has any comments on these things, and else I'm done. Thanks for listening.
Thanks so much for that wonderful talk. So if people have any questions.
Yeah, actually, I have a simple one. So, sure. You start with this ADS3, S3, T4, and then you deform the ADS3 in this particular way, right?
Yeah.
So do you know if it still preserves 4,4?
Yeah, it still preserves 4,4. It still preserves 4,4. The way we know is this way. Not from the coset side. Maybe it's also argued from the coset part, but it can be argued from here. So basically, when you do this J minus, J bar minus deformation, so basically you do this, right, in D2Z. And this has some operator on the space-time theory, D2X, D of X bar. So this operator is in the space-time theory. And this operator is the top component of the superfield, and it preserves 4,4. Of the space-time theory, yeah. I mean, this is basically, if you insist, this is basically sum over TI bar of the blocks. So you take the TTbar operator of the individual block, you add to the deform the individual block, and then take the symmetric product. That is what this D is doing. And this is known. This deformation is known to preserve 4,4.
Any more questions? Okay, if not, let's thank Soumangsu once again. And we'll see you guys next time.
Okay, thanks for listening.
Yeah. Thanks so much.
Yeah.